So, we look at the process of combustion, repeat some of the portions what you have done last time. You have seen that we can apply Bernoulli's equation 2.12 and 3.4, and since there is no bulk movement, there is no streamline flow at 1. So, we take V1 equals to 0 and V2, because that was at the top, V1 is inside and V2 is just outside at the hot gases, and V2 is what we are interested in finding, so that we can quantify the quantity of volume of flow. So, we take V1 equals to 0 and the hot gases is moving out. So, we take density of hot gases throughout, right, density of hot gases throughout, and write that equation. So, if you write this equation, P1, P2 expressions we had earlier in terms of y at any distance y from the neutral plane, and then we can then just simple algebra gives us V2 is equals to 2 rho 0 minus rho 1 divided by rho 1 gy, etc., to the power half. Now, rho 1 is nothing but we call it rho f, that is density of hot gases, rho 0 is that of ambient air, or similar, because everything whatever comes out will expand. So, we write this Vf, because this is the velocity, V2 corresponds to velocity of hot gases. So, Vf at any point y, hot gases, velocity of hot gases is this given by this kind of an expression, that is that is it's a function of y. So, this would be for the ambient air, this is for the hot gas, and at a distance y. So, we can find out. Similarly, we can do an exercise for 3 and 4, points 3 and 4, and here we assume the velocity V3 is equals to 0, because that is outside, 4 is inside, and like outside air, right, and here just inside the compartment where fresh air is just entering. So, this is the velocity of the fresh air coming in, and P4 and P3 was already available to us. So, therefore, we just put it, and since air is what is coming in, we take density of air throughout and replace this by rho, rho f. So, that is how we do it. So, rho 4 is rho f, right. So, putting f and 0 subscript, that is what we get. Overall it is rho 0, because hot cold air is coming in, and that is how we get the velocity at a distance y below the neutral axis of fresh air, right. So, mass flow of gases, therefore, one can find out by multiplying this velocity and integrating over 0 to h of, because it was something like this. This is I am calling as hf, that is neutral plane, and that is I am calling as h naught to 0. So, that is the I can integrate. B is the width of the window or opening, velocity as a function of y dy. CD is a discharge coefficient, because in we are assuming so many things. We are assuming it is a stream flow and applying Bernoulli's equation and all that. So, there has to be a discharge coefficient there, and this is a hot gases. So, density of hot gas. So, there is a mass flow of hot gases. So, B is the window width, CD is the discharge coefficient. Okay. So, that is what it is. Now, similarly, I can find out the mass flow of oxygen. Similarly, I can find out the mass flow of oxygen. CD rho 0 minus h 0 to 0, BB 0 y dy, etc., etc. So, now this mass flow, whatever hot air comes in, it must be reacting with the product of pyrolysis and producing the hot gases. So, the ratio of this mass I can actually obtain in terms of the say unit mass of product of pyrolysis reacts with R unit of oxygen, then 1 plus R would be the product. So, if R comes in, 1 plus R will go out. That is what we are assuming. And second thing is, another expression is HF plus H0 must be equals to capital H. So, these two ratios, if I look at it, integrate it from 0 to HF, then if I integrate it, I get it y to the power half. So, this y to the power half integration would give us y to the power 3 by 2 by 3 by 2, and rest all is outside the integral sign. So, I just put them there and simply find out the do a little bit of algebra. So, it is h to the power 3 by 2, h f to the power 3 by 2, and this one is there is this is rho f available here. This is actually this should be rho f actually. So, rho f to the power half, this is actually rho f, this is rho f. So, rho f and this rho f, it will come here, final expression turns out to be something like this. So, both these cases h 0 to the power 3 by 2, and there it was h to the power h f to the power 3 by 2, and rho 0 is here, rho 0 to the power half and rho 0. So, what we will get it this all of actually this will this ratio, of course, when I take ratio many of these things will cancel out. So, if I take ratio, this is how it is actually, this is fine, there is no problem, but that should have been actually rho f, this should have been rho f, this should have been rho f, this should have been rho f, because we are using that notation, rho f notation we are using. So, now I can find out that ratio, as I am saying, ratio of m dot f, the hot gases coming out and the air coming in, and this if I divide this ratio, if stoichiometric relationship is something like this, 1 kg of fuel reacts with r kg of water, producing 1 plus r kg of product, and for non stoichiometric burning I can use a factor that not all r is reacting, r divided by something is reacting, that is phi could be more than 1. In that case it will be 1 plus r by 5 kg. So, that is what it is. So, this ratio would be m dot by m air. I can find out this should, everything will cancel out, because this portion will cancel out, this portion will cancel out, this comes to the power rho to the power half, rho 0 to the power half, and this becomes rho f to the power half, this is rho so this cancels out, h f and h 0 remains, c d cancels out, 2 by 3 cancels out, b cancels out. So, I am left with this. So, this is the mass flow rate of hot gases outside by mass flow rate of air inside, right, air inside. Okay. So, this ratio if must be equals to this 1 plus r plus phi divided by r by flow, because this is the total product of hot gases. 1 kg of combustion or combustible or product of pyrolysis reacts with r kg of air or oxygen. Phi is a factor for incomplete burning. So, that much they will have some amount remaining as product of pyrolysis itself. So, this ratio if I look at it 1 by phi r, this must be equals to quantity of hot gases going out divided by quantity of hot gases, I mean fresh air coming in. So, this ratio is something like this, which you have just calculated, and if phi is equals to 1, putting I can get expression for h f by h 0 in this manner, because square up both the sides, this will become square, rho f by rho 0 I will be left with, and this will be to the power 3. So, h f by h 0 is given by this formula. Now, for h f can be written in terms of h naught, and we know capital H f plus h naught, and therefore, h 0 plus h 0. So, this is h f. So, h f plus h 0 I can write like this. So, this will be h 0 can be taken common, h 0 can be taken common. So, I can get h 0 by h, a factor like this from this relationship which I told you in the last class. I am just repeating this again, so that this is a little bit of algebra. So, I am repeating it for your better understanding. So, h 0 is 1 plus this, 1 plus this, 1 plus h 0 I can take common. If I take h 0 common, then I will get 1 here, this is like this. So, h 0 by h would be 1 over all this term, 1 over 1 plus all these terms, right. So, 1 plus this term. So, now as I said, typical values of R is 5.7 kg. That means 1 kg of wood, or when you burn wood, when you heat up product of pyrolysis, when you heat up the product of pyrolysis, right, product of pyrolysis, it consumes 5.7 kg of oxygen. Product of pyrolysis consumes 5.7 kg of oxygen. So, 1 kg of wood in a way consumes around 5.7 kg of oxygen. So, this value of R is 5.7 approximately. Typical ratio of rho 0 by rho f vary from 1.8 to 5. Rho 0 is 1.2 kg per meter cube. Fuel would be much less. So, this ratio is, so fuel would be something of like this ratio, rho f is smaller, say 1/8 of this, 1.8 divided by nearly. So, this ratio or 1/5 of this. So, which means that hot gases will have a density of 1.2 divided by 5 is how much? 0.24, and if it is 1.8, roughly nearly about 0.6, something like this. So, that is the density of the hot gas that goes out, right. So, this ratio is taken. Now, if I take average of this comes out to be 3.2. So, I can take an average value for this ratio, which is 3.2, put here 3.2, take phi equals to 1, R equals to 5.7, and then I get the ratio of H0 by F approximately for wood burning scenario. This value seems to vary from, I am repeating this from last class. So, that is why I am going a little bit faster. So, typically this ratio works out to be 0.34 to 0.42, 3.4 to 0.2, or for phi equals to 1, but in real case phi is not usually 1, it is somewhat higher. It is somewhat higher because burning would actually not all product of pyrolysis or all product will burn, something will go as unburnt product of pyrolysis itself. So, taking general empirical values has been seen as it is 0.3 to 0.5, 0.3 to 5. So, H0 by this is 0.3 to 0.3 to 0.5. 0.3 to 0.5, 0.3 to 0.5, all right. So, that's it. In other words, now I can actually relate everything, you relate everything in terms of, or H in terms of the capital H itself. Now, if we assume m dot is mf dot rate of material coming in is equals to rate of hot air, hot air going out is equals to rate of fresh air coming in, because mass within the space remains constant, then I can m dot air I can calculate out. I can calculate out m dot air. So, rate of oxygen coming in I can calculate out, which was given in terms of H0, which I have already, this expression was available to us. Now, I put H0 in terms of capital H, H0 in terms of capital H, because H0 was available in terms of capital H. So, I put it in terms of capital H, and if I get an expression for, m dot air in terms of H to the power 3/2 and B. Rest of the things are constant values. CD is the discharge coefficient. CD is a discharge coefficient, which is we know from various studies, empirical value, because there is no way you can theoretically derive and generally not theoretically derived. So, CD is known, G is known, rho 0, rho f we take as same ratio as 3.2, and so rho f, rho 0 values, roughly values are known to us. All that are related to the room is B into H to the power 3/2. What is B into H, or I can write it like this. What is this? That is the area of the window. So, area of the window into h to the power half. So, the mass flow rate of oxygen or mass flow rate of hot gases, which will be nearly same because mass remains constant, that is what we are saying, is a function of area of the window and square root of the height of the window. Now, remember ventilation factor I was mentioning earlier, empirical studies, I gave you a formula for calculating the equivalent fire resistance QF. This factor is called ventilation factor. So, the values are not important because a lot of them are empirical, but what I want to understand, I want to make you to understand is that the area of the windows or openings, total area of the openings and square root of multiplied by square root of the height, which we call as ventilation factor, that governs the rate of airflow into the room, right. So, if you have less, you will have less airflow into the room. If you have this high airflow into the room. Now, if it is less, what does it mean? It could be ventilation controlled. If it is very high, then it is simply controlled by the fuel. Now, the derivation is important to understand this one, but finally, what we are doing is we are taking so many empirical factors, ratio, averaging out for hot gases. So, what we take is a constant multiplied by this as a mass flow rate. This constant has been actually calculated out roughly, taking all the relevant values, like I said, take rho 0 by rho f equals to average value 3.2 and take G as they are. So, CD, appropriate value of CD. So, by doing all this, one can actually find out for density of air to be 1.2, CD is equals to 0.7, ratio of densities, so take A4 as the average, G 9.81. By doing all this for wood, actually one can get a value of 0.526 AWH to the power half. What is important to understand is that it is a function of this factor, ventilation factor, a constant multiplied by ventilation factor. We call this as ventilation factor. We call this as ventilation factor. We call this as ventilation factor. All right, call this as ventilation factor. So, this is important. This is very important. That is the factor, and this value is also important. This is kg per second. Everything 9.81 meter per second we have taken. Now, if I convert this into minute, I will divide by 60. Right? Convert this into minute. It will be divided by 60, and how much does it come to? 60.526 divided by 60.0, approximately it will be 0.0526 by 60. So, it will be somewhere close to 0.08 something, right. So, it is taken roughly as 0.09 AW, sorry, no, there is a 5.7, yeah. Now, taking just a minute. Taking phi is equals to 1 and 1 kg of wood and etc., the burning rate of the wood will be given by this. For wood, oxygen entry is this much, oxygen 0.526 AWH to the power half. How much will be the quantity of oxygen? This is the entry of air. How much will be divided by 5.7? Divide by 5.7, which is the stoichiometric relationship of wood and this. So, if I divide this by 5.7, we get 0.09 AW. So, this is the burning rate of the wood. Burning rate we have defined is the rate of production of product of pyrolysis, rate of production of product of pyrolysis. So, that is given by 0.09 AWH to the power half, which if I multiplied by 60, how much do I get? Which if I multiplied by 60, how much do I get? If I multiplied by 60, how much do I get? 5 point, yeah, something like that. So, kg per minute. So, therefore, burning rate of wood is given by 5.5 AWH to the power half, and if I in hours, then this is 330 AWH to the power half. What is the relevance of this formula? Supposing I know the total fire load in the room in terms of equivalent kg of wood. So, how long the fire will last? That total kg of wood in the room divided by 330 AW h to the power half. So, if I know like something like 50 kg per meter square floor area equivalent of wood, and my room area is, let us say, 30 meters square. So, total burning time will not exceed 50 into 30 divided by 330 into AW h to the power half, h to the power half, right, HW h to the power half. Okay. So, what you do when you have a number of windows, you will not have single windows. In fact, in case of fire, what happens is glasses breaks down. Hot gases, even if it is closed, it will break down. Glasses, unless toughened glass takes longer time, but many of the glasses would actually break down easily, unless it's a double glazed, a lot of other things can be there. But what happens is, or even if it's window, total window is available. So, what you will do, you will sum up AW. Generally, H is constant for all of them, and you can assume them in all in series, all are parallel. Basically, flow path is same, the potential gradient across them is same, pressure difference is same. So, they are parallel. So, parallel means you sum up all of them. So, AW sigma AW and h to the power half would be something like that. Everyone will have h to the power half. So, ventilation factor can be summed up, and you can find out, and if you find out this, then you can find out how much time it will burn. Now, this is okay, it's good, this understanding is good if you are doing fire design, but even if you are not doing fire design, in case of even planning, you know how much is the total burning time, what will be the rate of burning, and post fire assessment also this becomes important. This is what most of the time structural engineers or many people involved with investigation, because there is a fire, there has been a fire, you want to know how long the fire was there. Approximately you can estimate the fire load, and then use this formula to find out, well, maximum the fire could have been this if it was uninterrupted, no human intervention was there. But had there been human intervention, obviously firefighting etc., they would have reduced down. So, this is many assumptions, lot of assumptions. Important formula is this or this is what we will use, sometime we will use them later on also. This is the rate of production. If I multiply this by delta HC of wood, then I will get what? This by delta HC, I will get the amount of heat generated per unit time, rate of heat generation. So, this formula is important, but what is important is to understand the factors which affect the rate of burning and overall time of burning. So, this is called ventilation factor. So, this I definitely want you to remember, that AW h to the power half is ventilation factor, right. So, empirical relation of ventilation and ventilation factor, that is people have actually derived. What they have done? They have changed AW and h to the power half in furnaces, and they tried to find out what was the burning rate, because one can measure this burning rate as well, or heat generation or whatever it is. So, if MW burning rate of the fuel is more than MW rate of inflow of air divided by R, it is ventilation control. If if the burning rate, right, if the available, you can calculate out MB by this formula, right, you can calculate out MB, and MAR you can calculate out again. So, relationship is when the rate of burning is faster than air, available air, it will be ventilation control. If the rate of less air, it will be ventilation control. Whatever is the air, that will control the air entry, that will control the rate of burning. And when it is other way around, then it is fuel control. Lot of oxygen is available. So, you calculate out air rate of air entry using the formula. But people have done experiments actually. People have done experiments, right, empirically, then they have obtained some relationship. So, what they have found it, that if rho g 1.2 AWH to the power half divided by AF is less than 0.235, they have done experiments in compartment, AF is the surface area of the fuel, total surface area of the fuel, let us say in compartments. So, in our case we can say surface area of the fire load, total fire load, which could be floor area, surface area. So, then this is actually ventilation control, this is ventilation control. So, this rho g multiplied which is given by this formula. If it is rho g 1.2 AW h to the power half is greater than 0.290 is density of rho is the density of fuel, both these cases, density of the fuel itself, density of the fuel itself. So, this is actually fuel control. So, if this is greater than this, because this is air density of air, this is the density of fuel, this is the density of fuel, G obviously is there. So, one can calculate this out. So, if this is greater than 0.235 in a room, and this is the surface area of the fuel. So, in a compartment, whether it will be ventilation controlled in fully developed state or it will be fuel controlled, you can find out from this sort of empirical relationship, Now, this is, as I said, this is quite important. I mean, we have used it number of times in post fire assessment also. What would have been the case of fire, although the values there, these values are from empirical observation in certain type of furnaces, in controlled condition, but this some idea is definitely obtained, from even in case of post fire assessment and pre fire scenario as well, design planning scenario. So, this is what the experimental result is. What they have done, they have actually find out AT is the area of internal surfaces excluding the window area. People have measured, and this is the opening, they call it opening factor. So, I told you that I gave you that formula 0.067, remember that I gave you QF, the opening factor. This comes from this kind of an experimentation. So, people have done experimentation. So, opening factor is given by this. Temperature, they found that temperature increases, peak temperature increases with higher opening factor, and beyond the opening factor peak temperature tends to decrease. Now, some portion is fuel control, some portion is ventilation control, some portion is fuel control, some portion is ventilation control. So, this portion beyond left hand side of this line is fuel control, right, because this you can see the ventilation factor is AT divided by AW h to the power half. So, smaller this value is, higher this value would be, larger this value is, smaller this value would be. That means, you have more ventilation when you have small values of this. So, this zone is said to be beyond this peak is fuel control, because you have large value of this, because this value is small. AT is the total internal surface area, it is the total internal surface area. So, ventilation area is more compared to total surface area, that means less ventilation area, less oxygen flow. That is why this is fuel control, and beyond this is actually ventilation control, beyond this is ventilation control, all right. So, beyond this is ventilation control. Okay. So, this was from experimental compartment fire, experimental work, and 0.235 these values comes from those kind of scenarios only, similar and good. Right. So, we will break for a while and then go into the next aspects, answering your questions.